Hello NanoARCH 2022. My name is Owen Hoffend. I am a student studying at the University of Michigan Department of Computer Science and Engineering, along with my co-author Timothy Baker and our advisor John Hayes. Today I'll be presenting our paper on utilizing multiplexer-majority chains for managing correlation and cost in stochastic number generation. I hope you enjoy our presentation. For this talk, we'll begin by outlining some of the background from existing stochastic computing research. Our paper is primarily focused on the design of probability conversion circuits, or PCCs, which are a core component of stochastic number generators, or SNGs. We will see how two of the most common PCC types, comparators and weighted binary generators, are at opposite ends of an area and accuracy design trade-off. Next, we'll introduce multiplexer-majority chains, or MMCs, which generalize both types of PCCs and offers many intermediate designs providing better control of the accuracy and area trade-off. Finally, using two digital filtering case studies, we'll show how the proposed MMC design can offer an improved cost-to-performance ratio versus the two existing PCC designs. Stochastic computing is an alternative approach to digital computation that encodes data within random sequences of ones and zeros instead of using binary. A stochastic number x is a sequence of n zeros or ones with a value represented by px, the probability that any bit of x is 1. Therefore, a basic unipolar stochastic number represents fractional numbers in the range of 0 to 1. Given a bit stream, px can be approximated by counting the number of ones and dividing by the bitstream length n. The precision of a stochastic number is tied to the bitstream length. For instance, here we see three examples of stochastic bitstreams, each which approximates the value of 1/3. The longer bitstreams achieve values much closer to 0.33 repeating than the shorter ones do. A stochastic circuit generally consists of three parts: a set of stochastic number generators, or SNGs, which convert fixed-point binary numbers into stochastic bit streams of a desired length, followed by circuitry that performs computation in the stochastic domain, and finally a set of counters that sample the output bit streams, converting them back into binary. Circuits operating using stochastic numbers instead of binary tend to achieve better area and fault tolerance at the cost of lower precision and higher latency. For instance, a single AND gate multiplies the input probability values when the input bit streams are uncorrelated. Compared with an adder-based binary multiplication circuit, the stochastic AND gate multiplier has substantially lower area. The table on this slide shows a few other logic gates that implement useful functions, such as the mux-based scaled adder. Observe that when the input bit streams are correlated, these same components compute even more but different useful functions. Notably, AND, OR, and XOR gates respectively compute the minimum, maximum, and absolute value subtraction operations. There are many exciting applications that are currently being explored by the stochastic computing research community. Here, we will highlight two that are particularly relevant to our current research. The first is an example of a near-sensor stochastic edge detection circuit constructed using no more than 3 logic gates. It is able to produce convincing edges after only a handful of clock cycles, making it extremely power and area efficient, ideal for battery-constrained image processing environments such as mobile cameras or drones. The second application is a finite impulse response filter, or FIR filter, implemented using a mux tree architecture known as CMUX. In our work, we applied the FIR filter to an electrocardiogram signal denoising task. Both of these applications require their inputs to be correlated in order to achieve the best accuracy. In stochastic computing research, correlation between a pair of bit streams is typically measured by comparing the bit streams' respective values, px and py, against the probability of overlapping ones occurring, which is written px and y. This leads to the commonly used stochastic cross correlation, or SCC, measure, shown here in a simplified algebraic form. Using SCC, 0 is assigned to the uncorrelated case, and SCC equals plus or minus 1 is assigned to the fully correlated and anti-correlated cases, respectively. For example, here we see 3 cases in which a pair of bit streams x and y with probability values 0.75 and 0.5 are either fully correlated, uncorrelated, or anti-correlated. The overlapping ones are highlighted, and the corresponding overlap probability is shown. Generally, the higher the overlap probability, the higher the SCC. Unfortunately, efficiently achieving the desired level of correlation between bit streams is often challenging, and in practice too much or too little correlation is a main source of error in SC. Our paper focuses on the correlation and error implications of the stochastic number generator, SNG, component. An SNG consists of 2 parts, a pseudo-random number source, or RNS, typically implemented using an LFSR, and a probability conversion circuit, or PCC. The job of the PCC is to compare an input binary number to the RNS sequence and produce a stochastic bit stream whose probability is proportional to the binary input. Generally, uncorrelated bit streams with SCC equals 0 can be generated using an independent RNS for each SNG. To generate correlated bit streams, the prevailing technique in the SC literature is to share a single RNS among multiple PCCs, as shown on the right. This architecture also dramatically reduces the overall area dedicated to random number sources. To convert a stochastic number back into binary, a counter is used to sample the bit streams over n clock cycles. This produces an estimate of the target output function from which overall circuit error is found using the mean squared error or MSE measure. It can be shown that the error due to improper correlation usually dominates the MSE as the bitstream length increases. There are two commonly used designs for probability conversion circuits. The simplest and most commonly used PCC type is a binary comparator, which outputs a 1 if the input value is greater than the RNS value. Another design is the weighted binary generator, or WBG. The WBG is a two-stage circuit whose implementation is shown. WBGs have the advantage that they are lower in area and that the first stage of logic can be shared among all SNGs for further area savings. For example, a single 8-bit WBG is 32% lower in area than its comparator-based counterpart, and the area reduction improves as more WBGs share the same stage 1 hardware. The downside of WBGs, however, is that using them for some designs such as scaled addition and especially edge detection results in substantially higher error, as shown in the plot on the bottom right. This error discrepancy can be explained by the fact that the WBGs fail to generate correlated outputs when the RNS sharing is used, thus causing correlation error for circuits that expect correlated inputs, such as the edge detector. This implies that switching between a comparator and WBG-type PCCs trades off accuracy for area. Next, I'll introduce our proposed multiplexer-majority chain design, which generalizes both types of PCCs and offers many intermediate designs providing better control of the area and accuracy trade-off. To understand how PCCs of different types are related to one another, consider the general equation for the output probability of a PCC given here. The equation states that the output probability of a j+1 bit PCC is the average between one of the binary input bits, pj, and the output of a smaller PCC with only j bits. The recursive form of this equation suggests that PCCs may be constructed as a chain of stochastic averaging circuits. The mux gate computes the exact averaging function we need, 1/2 x1 plus x2. Thus, it can be shown that a chain of muxes connected as shown in the upper right forms a WBG-type PCC. To perform a comparator using the same equation, we construct a similar chain out of majority gates instead of muxes. Majority gates output a 1 if 2 or more of their inputs are 1, and prior research has shown that they implement the same averaging function as muxes when one of their 3 inputs has the value of 0.5. Majority gates are known to have a higher area cost than muxes, which is consistent with our prior observations that comparator-type PCCs have higher area than WBGs. Additionally, it has been shown in prior research that majority gates tend to have a higher output correlation than muxes, which is again consistent with the lower correlation error of comparator-type PCCs. This trade-off can be generalized by introducing a parameter k, which specifies the number of mux gates which are replaced with majority gates for an n-bit multiplexer-majority chain, or MMC. Under this MMC model, a WBG has the minimum number of majority gates at k equals 0, while the comparator has the maximum at k equals n-1. Here, we show two 5-bit MMCs, the first with k equals 2 majority gates, and the second with k equals 3. We've found experimentally that the best accuracy results are always achieved by replacing muxes from right to left, starting at the last one and working backwards. In the following slides, I'll discuss the area accuracy trade-off of MMCs. First, we'll look at the area results for MMCs. The graph on this slide plots normalized area on the y-axis versus the number of majority gates k in an 8-bit MMC on the x-axis. The different colored lines show how many PCCs are generating stochastic numbers using the same shared RNS. To maintain consistency, our area numbers are reported on a per SN basis. This data was generated using the Synopsys design compiler using a 45 nanometer cell library. The k equals 0 and k equals 7 cases represent the WBG and comparator PCC designs respectively. As I mentioned earlier, the WBG design both has lower area overall, and its area cost decreases as the number of shared RNSs increases. As expected, the comparator design has the highest area. In between the WBG and comparator designs, we observe that the area cost is approximately linear with respect to the number of majority gates K. We now move on to analyzing the accuracy trade-off of MMCs. Since accuracy is highly dependent on the circuitry which follows the SNG, a better stand-in measure is correlation. Our paper focuses on circuits expecting correlated inputs, and for these designs, higher input correlation will usually yield better accuracy, and vice versa. On this slide, we show heat maps of the expected output SEC value of the two MMCs while varying the SN values Px and Py, as well as the K parameter. When K equals 0, that is, the PCC is the WBG, the heat maps exhibit a fractal-like pattern that fluctuates wildly between SEC equals -1 and SEC equals 1. Each time we increase K, we can see that half of the remaining fractal pattern is replaced with area of solid SEC equals 1. Thus, increasing K by even 1 or 2 results in dramatically more consistency in terms of output correlation. This culminates in K equals 7, where the PCC is a comparator type and the correlation is always exactly SEC equals 1. To better visualize the correlation trade-off curve, we can compute the average SEC over all possible input value pairs, under the assumption that each value pair is equally likely, i.e. the input values are independent and identically distributed uniform random variables. The resulting graph is nonlinear and confirms that SEC rapidly increases after increasing K by just 1 or 2 majority gates, with diminishing returns as we get closer to the comparator design. In other words, adding just a few majority gates to the MMC has a dramatic impact on the output correlation. Since circuit area is only increased linearly with K, we can utilize MMCs to exploit this favorable SEC trade-off to achieve high SEC and thus high accuracy, with a comparatively small relative increase in area at cost. I'll now present 2 case studies that show off the performance characteristics of MMCs when they are used within practical stochastic circuit designs. In our first digital filtering application, we utilize an architecture called a correlation-enhanced multiplexer, or CMUX, to implement a low-cost FIR filter and investigate how CMUX's area and accuracy vary with its MMC parameter K when implementing an electrocardiogram ECG denoising task. For each K value, we found the entire circuit's area using Synopsys Design Compiler and measured the accuracy in terms of signal-to-noise ratio, which is a more realistic output metric than either correlation or MSE. The results show that when WBG PCCs are used with K equals 0, the area reduction is 40% compared to comparators, but the SNR is 25% lower. In contrast, using MMCs with K equals 1 yields the best trade-off, where a significant 30% of area is saved in exchange for only 7% lower SNR. Our second digital filtering application is median filtering, which is effective at filtering out impulse noise types in images. For our experiment, we implemented a 3x3 median filter kernel constructed using a network of AND and OR gates, which implement the minimum and maximum functions, respectively, when their inputs are correlated. To evaluate the filter, we corrupted 10 different test images from the MATLAB image processing toolbox with random salt and pepper noise. The images on the right show an example output. With K equals 0, a fair amount of noise remains in the image, especially in the lower half. When K equals 4, the result is virtually indistinguishable from the comparator design. To evaluate the accuracy of the median filtering circuit, we used the Structural Similarity Index measure, or SSIM, which is designed to better capture perceptual differences between images relative to MSE. An SSIM of 1 indicates 2 images are visually indistinguishable. We again used Synopsys Design Compiler for our area measurements. For this design, the best K value was K equals 4, which yields an SSIM of 0.965, which is very close to 1, with an added benefit of a 10% area reduction. Note that SSIM accuracy curve does not achieve diminishing returns as quickly as the FIR filter signal-to-noise ratio curve did, or the MMC correlation curve from earlier. We found that this discrepancy is due to image pixel values not being necessarily independent and identically distributed uniform random variables, which was the assumption we made previously. Instead, they tend to correlate with one another in a local 3x3 window on actual image data. To wrap up the talk, we'll discuss some key takeaways from our research. In this talk, we demonstrated that area-efficient WBGs do not generate SCC=1 suitable for correlation-reliant designs. To improve stochastic number generation for such designs, we introduced the MMC-PCC design, enabling flexible area correlation trade-offs. We then showed two case studies illustrating the subtleties of the area accuracy trade-offs offered by MMC-based PCC design. In general, our recommendations for SC designers are that if the design requires inputs correlated at SCC=1, the use of MMCs should be considered, and the parameter k should be chosen on a case-by-case basis depending on the desired area-to-accuracy ratio. The expected input value distribution to the circuit should also be factored into this decision if it is known. As we have seen, it has a non-trivial impact on the trade-off curves. If SCC=0 is required, we recommend using separate RNSs to maintain uncorrelated inputs and use WBGs for the best area. To conclude, our work expands the number of options available to SC designers for producing efficient stochastic number generator designs that are custom tailored to their applications. That is the end of this talk. I hope you enjoyed our paper on multiplexer majority chains. Are there any questions?